BCPNN stands for the Bayesian Conference Propagating Neural Network. It is a special modification of the naive Bayes framework, and it is a neural network form of naive Bayes basically, with some certain additional modifications. So first we will describe the first uh, or one layer naive Bayes neural network. Um, so naive Bayes. Here the goal is to maximize the probability distribution of P of y given a vector x. So suppose we have some parameters to estimate uh, all the necessary information required to estimate this probability. Given a new vector x, we wish to estimate the conditional distribution P of y given x for all values of y, and assign whichever value of y gives the maximum of this probability. This can be written in the form of P of x given y to P of y by P of x by Bayes rule, and if we want, we can also transform it into the joint divided by the condition divided by P of y and P of x. This is just the definition of the conditional distribution P of x given y. So we want to transform this into a neural network form of neural network. This probability should be represented through a neural network. And what does a neural network do? It has neurons where it takes in the sum of the input activation and adds a bias and produces an output or a support. So this neuron, let us just name it J, and let us call this I, and let us call these weights WJI. So, and this support SJ. So to calculate SJ, what we do is we take the input activations OI, we multiply a weight, scalar weight WJI, we take the sum over all possible neurons of I, add a bias Pj, and we get the support Sj. This support is we can see it's a linear, this is a linear equation basically. We can also convert the support into a non-linear form using some softmax or some activation like ReLU, etc. So basically we have to transform this somehow into a more suitable form for this neural network, so that this can be represented. This is similar to this basically. Let us start by transforming this equation into a linear form by taking log. on both sides. So log of p of x and y, p of y, p of x, p of y, plus p of log of p of y. Okay. Now, the naive Bayes assumption is basically the conditional distribution p of x given y can be factorized into its components p of xi given y, I ranging from I equals to 1 to d. So suppose x is a d-dimensional vector, then we can take the product of each probability p of xi given y, multiply all of them to get the probability distribution p of x vector given y. This is the naive Bayes assumption. It is just basically the conditional independence assumption. So this this can be actually changed to a more suitable form. Log p of y given x equals to log product of y equals to 1 to d. Remember, this is basically again the joint, the conditional distribution p of x given y divided by p of y, that is. So you get, p of x, p of x I given y divided by p of x. Yeah, so what you've done is actually just taken this one, this form of the equation, disregarding this. Just take p of x vector given y, and we write it as the product p of xi, product of p of xi given y. Also, we assume in this, since I've written p of xi, I've also assumed p of x can be factorized into its products. These two are not equivalent assumptions, and neither one implies the other. This is just the independence assumption, and this is the conditional independence assumption. So the log of the product, we have the log of the product, and we have a sum here. So we can write this term as sum from I equals to 1 to d, since log of product is equal to the sum of the log. Yeah. So the idea here is basically, suppose we want to model the support as log of p of y given x, and suppose we have, through this sum, we somehow model it as log of p of xi given y and p of xi, and the bias as log of p of y, then this term and this term is similar, and we can represent this in terms of a neural network.